thanks for stopping by. First presentation of today is again a very technical topic. It's about PTP, and the question is raised quite often: do we actually need PTP for our, operations and applications? And the question is, why do we probably need it or do not need it at all? And so I have looked at different streaming technologies and protocols, and I'm comparing those with its capabilities and how they work. And at the end, we will answer the question, do we really need PTP or not? Right, let's jump into the topic. The first few slides are to set the scene to really understand what this is about. First of all, we need to quickly look at the general requirements in professional broadcast applications. From the audio point of view, because audio is the most complicated thing or the most accurate thing at all, video is some more relaxed. So audio has the highest precision requirements, right? We definitely want to have the ability to transport media bit transparently throughout the facility. That means we don't want to have sample rate conversion employed, well, as a necessity, right? And that in turn means that all streams running around need to run on the same media clock or sampling clock, because if not, we need sample rate conversion, to process the audio. We also on a network want to have the ability to run different clocks on the network, but of course streams can only be transported between devices with the same clock setting. But of course we want to be able to have 44.1, 48, 96 streams running around on the same network and not limit the whole network to something. We also want to have determinable low end-to-end latency and the ability to time align streams among each other, right? Simple example, left stream, right stream, captured individual by a left network microphone, a right network microphone. We want to be able to sample accurately align them at a receiving point. And of course, we want to replace the old traditional house clock distribution. We don't want to have a network and then the house clock distribution as an add-on, right? We want to replace the house clock functionality on our network as well. So, and from these requirements, there's a clear consequence. The traditional clock reassembly from just observing an incoming stream and trying to regenerate the media clock, the inner media clock, is not applicable, of course, due to those requirements we have here. By the way, that is called the asynchronous operation. Asynchronous because it's just one stream which is asynchronously running on the network compared to others. The distribution of master clock beats from a master device is also not sufficient because it doesn't carry time information. We can operate in a synchronous mode, so all devices are on the same clock frequency, but we don't know anything about time, so we can't align those streams. Yeah, and consequently, a common understanding of reference time is required. That's the wall clock. So we need some sort of wall clock which has an absolute time in the background, and that is what we call the synchronous operation mode. A quick look at the accuracy requirements. Audio applications, as I said before, have the highest time accuracy and precision demands. We definitely want to have the ability to sample accurately align incoming streams compared to each other. So that means we need a precision which is better than half a sample period. Just a quick illustration here. Let's say the transmitter has a sample period. I should have a pointer here, right? A sample period which relates to a full sample. Then we have a receiver which has its own media clock. Let's say that is off by half a sample period, so that particular sample would relate to this arrangement or alignment. And then we have another receiver which is off in the other direction by half a sample clock, right? So as a result, we will have close to one sample clock misalignment between any two devices in the system, and we don't want to allow more, because if we allow more, then we can't have a sample accurate alignment anymore. So the requirement is we need to have a precision of at least half of a sample period in the whole system, which translates at 48 kilohertz to 10 microseconds. And if we go up with the sampling frequency, it's even tighter requirements, as you can see. Now, the other point we definitely want to have, and brought it up earlier, is the distribution, the replacement of the word clock distribution. Now, for word clock distribution, we have a standard which is AES 11, and that calls for a maximum of plus minus 5% of accepted jitter or wander. Right, that's just an AES11, that's a standard. So in a diagram, this looks like this. We have a media clock at any certain device in the network, and any other device acquiring or adhering to this standard does not have a larger offset than 0.05 of the media clock amplitude. So that translates in even tighter numbers at 48 kilohertz. That means we need to have a precision of at least 1 microsecond or better in the system. At any point in the system, 1 microsecond in terms of absolute time. And we go up with the sampling frequency, we have even tighter requirements. So that's just to set the scene what requirements and what precision we need in a system. That's not necessarily in media, a network media system. We have that in any sort of system. Now, let's have a look at the technologies I'm comparing in this presentation. We have the plain old traditional RFC 3550, the real-time transport protocol. Then we have the well-known RAVENNA AES67 or SMPTE 2110 way of distributing synchronization information and streaming, of course. Then there's AVB, an IEEE standard, audio video bridging, which these days is named TSN, time-sensitive networking. And finally, we have the new kid on the block, which is IPMX. So let's have a quick look at how the generic RTP clocking with RFC 3550, the whole asynchronous case, works. We have a sender, we have a receiver. The sender has its own either free-running or externally driven media clock, which is used to sample the media data, right? So it's acquiring information by a free-running internal media clock or by an externally supplied media clock. The clock, the stream data, the samples are sent over with the RTP stream clock. The RTP stream clock, which is part of the RTP protocol, is directly derived from that media or sampling clock. So in other words, the samples in the stream clockwise relate to the acquiring media clock, right? So next, you need to know that in RFC 3550, the relationship of the RTP stream clock and the related media clock may have a random offset. That's for reason of trying to provide crypto attacks on secured streams. Don't want to dive into this. It's just so that the standard calls for the ability to have a random offset in the media clock values. Now, the receiver has to restore basically the media clock, which is inherently transported with RTP. So first of all, it needs to receive the RTP packets, and it needs to build some sort of a buffer in order to cope with any sort of jitter and whatsoever. So there's a configurable delay or buffer on the receiver side. Then the receiver, the most common mechanism is that the receiver is starting up with a nominal media clock, which is adjustable, and it's adjustable by looking at the fill level of the receive buffer. So it's starting to assume, let's say I'm having 48 kilohertz as my media clock on the transmitter side, and it's observing how this fill buffer is either increasing or decreasing. If it's decreasing, apparently my media clock is too fast. If it's increasing, my media clock is too slow. So it's adjusting its own media clock by observing the fill level of the input buffer. That's a very common traditional scheme. And then once the media clock is, permanently adjusted, it's a permanent process, it is also used to play out the media samples from that buffer. And so by that, I have very closely resembled the media clock of the transmitter. Well, the main benefits and drawbacks of these mechanisms are that I can use basically any input signal or any media clock, can transport that inherently with the RTP stream, and it can reasonably well resembled at the receiver, depending on the quality of the sender and receiver clock circuitry and the algorithm which observes the fill buffer level and so on. The drawback definitely is I don't have the ability to concurrently process any two independent streams because every transmitter is running on its own internal or external frequency, and I cannot assume that they're running on the same frequency. So if I have two incoming streams, they definitely run on different frequencies, and I would have to have two adjustments or two clocking mechanisms to actually, clock these independent streams. Or I would employ an SRC, which is now then destructing the bit transparency. So I don't have the distance anymore. And of course, I don't have any deterministic latency because I don't have any absolute time information. I can build a, configure the playout delay and everything, but I can't do it inherently by, having some system information. So that's definitely a drawback. So there's no alignment between streams. Now, with the RTP clocking, we don't only have this asynchronous case with free running clocks, we also can employ the synchronous case by supplying an external clock reference to all the devices. So we have this picture again. See, that's quite the same picture. What we do now, we provide a system-wide reference clock to all the devices. So now the sender and the receiver clock are running on synchronized media clocks. So we know the frequency of all the media clocks inside the devices is absolutely the same. And so that is that we don't need this buffer observation anymore. And the delay we are configured is a constant, and at the end, deterministic delay. It stays at that value, and sender and receiver operate in a fully synchronous way. That means, of course, in turn, that since now all media clocks are following the common reference clock, I have the same media clock for all streams, right? That means that concurrent processing of independently received incoming streams is now possible, although we still don't have any time alignment and most likely also not a phase alignment. Phase alignment might be the case, depends on the precision of the whole clocking system, but we definitely don't have a time alignment. And because we don't have time alignment, there still is not an absolute deterministic latency setting. Well, we can adjust it, of course, individually per stream at any receiving device, but it's not per se deterministic upfront. But once it's set, it's stable. So, and then there's a third scheme with RTP, which is clocking involving the so-called RTCP sender reports, which works for linear audio, for linear PCM audio. This scheme with the RTCP sender reports can work with a common reference clock, a wall clock of any sort, any type, or without a common reference clock. And how this actually works, I will save that later for the IPMX section, because that's one of the core features which has been defined just recently with IPMX. So stay with me on this one. Let's have a quick detour into AES67 synchronization, because that's the next level of synchronization on a network. AES67 is based on the fact that all nodes are running local clocks. The local clocks are precisely synchronized from a common reference clock via PTP. So here's PTP coming into game. And once I have synchronized local clocks, I can generate media clocks independently at every device. And since when I have accurate or precise enough local clocks, the media clocks independently generated by every device are all the same. And not just in frequency. If it's the whole clocking mechanism is precise enough, we have also a phase correlation of these clocks. A quick picture of that, how that works. We have a master clock on the system that may or may not be referenced to GPS. That's just an application dependency. We have those slave clocks or follower clocks in the devices. They are synchronized through PTP. And if they are synchronized, all the locally independently generated media clocks look all the same, and they are actually most likely also phase correlated. So we have wonderful, nice media clocks. Here's the diagram with the sender and receiver again. There's the wall clock, the sender and receiver. Both devices have their local clocks. PTP is used to discipline these local clocks. So they basically reflect the instance of the wall clock. I generate media clocks from those local clocks, right? And of course, sender and receiver are doing that. all devices are actually doing that. And then I use that media clock to sample media data, the audio data, the video data, whatever, and transport it with an RTP stream. And again, the RTP has its own RTP clock, but that in AES67 or 2110, whatever you name it, is related or derived directly from the media clock again. Also with the random offset stuff, which is part of the RFC 3550 definition. And then the receiver has the very same mechanism, but in order to have the absolute time information, so that it actually knows when a incoming sample has originally been created, so that it knows when to play it back, it needs the information about this random offset, and that is conveyed out of band. It's not part of the RTP protocol, but it's in the SDP file. So if anyone ever has looked or dealt with SDP files, he had seen that information in the media clock attribute where it tells the system, okay, there is an offset with this particular stream, and once the receiver knows that offset, it can perfectly time align the desired playout time against the reference wall clock. And we have an inherent, absolute deterministic and alignable stream processing in the system. And the only difference between AES67 and 2110 in that respect is that the folks at 2110 said, okay, we don't understand why there could be or should be a random offset per stream. We constrain this by defining that every 2110 stream has to run with a 0 offset, so that I don't have to convey this in the SDP file. So it's inherently known, there is no offset, and all the RTP clocks of every stream in the network adhere to the very same origin point in time. That's the only minor difference, not a big deal here as well. So how do I receive the deterministic play out? Let's have a look at the AES67 synchronization model again. The magic is the link offset. So here we have a sender implementation, we have the network, we have a receiver implementation, and you can see the timing reference planes. At the sender, we have this ingress reference time point. That's the point in time when a sample is taken. And at the receiver side, the egress reference time point, that's the point where a sample is forwarded to, the audio interface, the processing stage, whatsoever. And the time between the ingress and the egress point is called the link offset. Now, how can the receiver now calculate the exact point in time when to play out any received sample? Well, it has the RTP timestamp, which tells basically when a sample had been created at the sender. It takes the desired link offset and adds it to the RTP timestamp. It subtracts and eventually offset and an optional offset from it. So if there's an offset conveyed with the SDP file, it subtracts that value again. And this simple math gives you the exact point in time when this sample needs to be played out or forwarded to the playout stage on the receiver side of things. And if the sample is arriving at the receiver earlier than the playout time, well, it needs to be stored in the receive buffer, of course. Right? And by that, the whole system between ingress and egress is absolutely, constantly, and deterministically coupled. Same frequency at absolute deterministable time. So, main benefits, main drawbacks of the AES67 2110 synchronization scheme. All media clocks are basically following the common reference. There's an accurate reproduction of the reference clock at all nodes, and we have an identical phase media clock for all streams running around the network. And that means that we have concurrent processing capability at all the independent nodes, because all streams follow the same clock and follow the same time. Through the time information, the time relationship, we have deterministic latency and the ability to sample accurately align play out of any two incoming or any number of streams, actually, even across different nodes. So the left and the right microphone gather events can even be played out, transported and played out independently at the destination speakers in the system. And they would absolutely sample accurately play out. Or you can deliberately apply alignment delays. If you have, let's say, the positions of the speakers being a little bit behind, a little bit back, you can just calculate for the acoustic delay and tell one speaker, to have a bit more deterministic playout delay than the other. So you get the delay loop or the delay device for free, actually. All right. The drawback, of course, is any asynchronous input signal needs an SRC on the input side. Example, if I have an HDMI input signal, which is originating from a freewheeling device, and it's not synchronized to the whole AES67 network, well, the only thing I can get that on a network and transport it and process it is an SRC with that inherent network media clock and the beginning, right? There's no way of ever transporting an asynchronous signal across the network and process that at some receiving point. Okay, then the next big thing in the standards, in the way of network operation schemes is AVB, audio video broadcasting. For those who have never heard about AVB, it's a layer 2 standard Ethernet extension to achieve guaranteed and precise media transport in Ethernet environments, which require those extensions to be supported by the network infrastructure by switches. But it's interesting to look at the way the synchronization is achieved. I'm not starting a discussion about the benefits and drawbacks between AVB and layer 3 transport. Just interesting to see how they achieve synchronization. Now here's a typical picture of a talker. The senders, their slang, it's a talker. Now the talker has a clock. That clock is actually synchronized by it's coming here, is synchronized by GPTP. It's a variant of PTP. So the clock, the input clock, may be free running or following an external device, and we have a reference clock which is not synchronous to the media clock. So we have an asynchronicity between the media clock and the reference wall clock, right? But the key now is that the incoming samples are time-stamped with the reference time. So the sender exactly knows, here's a sample with respect to my reference time. Here's a sample, next sample with respect to my reference time. Now we have the information how far apart each clock cycle actually is with respect to the reference time clock. And that is what we use in AVB. We are basically also packing a number of samples into a packet, and the timestamp information of the first sample of that packet is put into the packet as well. So that is conveyed over to a potential receiver or listener. That's how they call it in AVB. So the listener looks pretty simple. Again, this has a wall clock reference, it has an input receive buffer, and it has a media clock. Now the trick is, with AVB, the receiver regenerates the media clock of the incoming stream from the timestamp information, which are referenced to the common network reference clock, right? So it now needs, can see, okay, I have, let's say, 16 samples in my packet. The timestamp was, whatever, T1. The next packet, which is exactly 16 periods of the incoming media clock later, has another timestamp. And it's a simple math calculation by subtracting T2 minus T1 divided by 16. And then I exactly know what is the, what is the resulting frequency for the media clock I need to rebuild. So that actually allows the AVB system to transport any asynchronous media clock, and the receiver is able to exactly rebuild that input clock. So the difference between AES67 2110 and AVB is AES67 always has synchronous media clocks everywhere. AVB has just the reference clock time everywhere, but has free running asynchronous media clocks or sample frequencies. Now, what's the main benefit and drawbacks with AVB? It can deal with variable input clocking. So it does not have to apply a sample rate conversion to take any, any possible input clock. It has a deterministic latency because we have absolute time references. AVB works with presentation times instead of generation time, but basically it doesn't make much difference. It's just that the sender already imprints presentation time desired presentation time. Usually that's 2 milliseconds plus or offset from the generation time point. That's for ease of use of the whole system. I don't want to dive into this. But another benefit is that there's a precise reassembly of the input media clock. And of course, that again depends on the precision of the clock circuitry. The whole system is sender to receiver is frequency locked, most likely not phase locked. But that's basically the benefit. But again, since every stream may have its own independent input frequency, I don't have the option to concurrently process independent streams again, because any stream has its own media clock deviating from each other, because, well, the talkers, the senders are free running, unless they have some sort of additional synchronization, right? And in order to have the ability to run a fully synchronized location or facility, AVB provides the option of running a clock reference stream around. So unlike AES67, which takes the media clock from the clock directly, they are now running a clock reference stream around all the devices, and then the devices need to rebuild this media clock just the same way receivers would rebuild the media clock from an incoming stream. So now also the senders need to rebuild the media clock, and then they sample their input signals with a media clock which is common to all devices. And this way we have now the option of a fully synchronized operation in the whole network. But again, that requires that we have a common reference clock stream running around. And this basically is what Milan, don't know if many of you have heard about Milan, but Milan is a layer on top of AVB, and they have defined this mechanism and are using it to achieve the full synchronous operation as we have with AES67. Again, they are not losing the capability of running asynchronous signals, they just can't process them together. Okay, now finally we have this new magic on the block, IPMX. IP Media Experience. What is IPMX? IPMX is an initiative by AIMS and is basically looking at applying the available open-based standard protocols to the Pro AV industry, matching their application requirements. So it basically specifies on the basis of 702110, but adds further specification and enhancements. And the most important for us here today now is that they have added something they call enhanced or relaxed timing requirements. And that's the point of the whole presentation, actually. And of course, they are also taking other functionalities like HTTP and network discovery registration, I/O management, closure, contact. All these go into IPMX, and it's not part of this particular presentation. So basically, the goal of IPMX is building a basis, providing a basis for simple deployment, and only requiring basic networking equipment knowledge. We'll see. So, internally, in the agenda, IPMX says we are thriving to support the full range from professional applications we typically have in live production systems, so that means 2110. So they inherit 2110 with large synchronous AV systems, but also include the one-to-one HDMI connection over IP. So this is the whole range of things IPMX thrives to cover. In broadcast, devices typically are locked to this, house clock, reference clock, and in non-broadcast AV, you more often have asynchronous signal transfer. So basically, you see the need why they are trying to incorporate everything of both worlds. And as a result, IPMX standard supports the operation in networks with and without PTP availability. So IPMX, as it's being defined, can be run on networks that have PTP, most likely the large broadcast operations, or which don't have PTP, the smaller AV environments. So it specifies what to do in the presence of PTP, but also specifies how to operate when PTP is not present, right? And That's the IPMX standard, but that means since IPMX supports both cases, that all IPMX devices definitely need to support both methods. Because if they are not, they could not support one or the other operational mode, right? So the devices, for the device implementers, this is a huge task because they have to include all the operational capabilities. Just for the application, you have the freedom to choose PTP or not PTP. When we read the VSF TR10 drafts, which have just been published on the VSF.tv site, so they are now available for download, you may come across some ambiguities on several aspects. On one hand, it says PTP shall be supported. On the other hand, it says, well, but it's not required in simple applications who do not need alignment and these kind of things. And, thus does not need to be supported at all. Well, no, that's not the case. It definitely needs to be supported, as I just mentioned earlier. But then also there's a requirement stated IPMX receivers shall be able to recover the asynchronous signal timing and produce an output that is frequency locked to the IPMX sender, regardless if PTP is present or not. I mean, we know how this works with PTP. But are we really sure that it works with not PTP? Well, yes, we have seen how this works. RTP can do this, right? The standard 3550, so IPMX can do that as well. However, they are not telling you how to do this in the standard. That's the way standards are written. They specify something, but they don't tell you how to implement it. And then there are some ambiguities in the stream alignment requirements. The stream alignment requirements refer back to 702110 or the AES67 link offset, which I explained earlier. That's back. Where's back? Previous. I'm sorry for that. Okay. This is. Oh, I'm lost. Previous.
What's up, dude?
Yeah, I know. Right and left mouse click is always a bit difficult here.
Here, just hit this guy down here.
Ah, here, yeah, okay.
Yeah. It's backwards.
Yeah, I want to go back first. Okay, I need to this one again. It's not bringing this one. Doesn't matter. Anyway, so the problem actually is. We need to look closer and see how the requirements set forth in IPMX can actually be implemented on the implementer side. So basically, IPMX defines at its core 3 synchronization mode. It's the 702110, where all input signals are synchronized to a common reference clock. That's the AES67 synchronization. It also defines the full asynchronous mode, where we have an asynchronous free-running signal, RFC 3550, RTP. That's also part of IPMX. And I promise that I will bring up the RTCP information, which is actually very similar to the AVB type of implementation. That's why I brought up the AVB type clocking. Now that's the picture of the AVB clocking synchronization again. Remember this. And now the only differences actually are, instead of a GPTP wall clock, we have a layer 3 PTP wall clock, 2110, AES67 PTP wall clock. And in terms of, instead of 7022 Ethernet transport protocol, we have RTP. And everything else is pretty much the same. We have that asynchronous input clock there. We have the RTP timestamp generator, and driven by the PTP clock now. And if we look at the PTP packet, of course, this data goes into the data part of the RTP packet, and the timestamp, which relates to the first sample of that data, just like with AVB, goes into the RTP timestamp field. So we have now an RTP packet with the timestamp information and the data, and now the reference to the absolute wall clock comes into game, because that is all relative stuff here. The reference comes into game with the RTCP timestamp. So the real actual reference timestamp cannot be transported in the RTP packet. That can be transported by RTCP only. I know. And then we have the PTP absolute time information and the RTP time information in the RTCP packet. There's always one RTCP packet per RTP, and so the receiver has the information how these incoming packets relate to absolute time reference. Okay, that's basically that. And as always, I'm running overtime. Let me bring up two resulting slides. The question at the end, do we really need PTP? Well, PTP enables precise clocking, synchronous operation inside of the complete system, transport of synchronous and also asynchronous signal inputs with SRC, perfect alignment of any streams anywhere on the network, but it most likely has a more complex network design because it needs to run PTP. Without PTP, we have most likely a less complex network design, but we lack the ability of having a full synchronous operation or deterministically time align the asynchronous streams. So graphically represented, functional advantages would vote for, from the view of functional advantages, would vote for PTP. If you say, okay, I want an ease of use, you probably go without PTP at all. And yeah, wonderful. That's it. Sorry for being late, a bit overtime, but we started late. Might not be everything quite clear at the moment. I'm here to discuss anything. Anyone who wants to discuss anything any further, I will be here for more questions, which we can't take at that moment.
Thank you.